Welcome back to Tech Tutors. Today, we're exploring the powerful data structure, arrays. Let's begin. So, what exactly is an array? An array is a static data structure that stores a collection of elements, each identified by an index or key. Arrays are designed to hold multiple items of the same data type in a contiguous block of memory, which makes accessing and modifying data very efficient. Here are a few key points to remember about arrays. In an array, indexing starts at 0, which means the first element is accessed with index 0. The size of an array is set when it's created and cannot be changed later. Additionally, all elements in an array must be of the same data type, whether they are integers, characters, or even other arrays. Arrays come in different shapes and sizes, primarily classified into two types. One-dimensional array, also known as a linear array, it's the simplest form of an array. Imagine it as a list where elements are accessed with a single index. For example, array name stores 5 elements that you can access using indices 0 through 4. This type of array is ideal for storing sequences of similar elements, like a list of numbers. Two-dimensional array, often referred to as a matrix or table, is an array of arrays. It requires 2 indices, one for the row and one for the column, to access an element. For example, array name represents a matrix with 3 rows and 4 columns, holding 12 elements in total. Two-dimensional arrays are perfect for representing tabular data like spreadsheets or matrices. Let's break down some of the key characteristics of arrays. Once an array is created, its size cannot be changed, meaning the number of elements it can hold is predetermined. Each element in an array is accessed using an index, which typically starts from 0. This allows for fast and efficient data retrieval. The elements of an array are stored in consecutive memory locations, which enhances the speed of access. While we often think of arrays as static and fixed size, dynamic arrays can be implemented through specialized data structures or libraries that allow resizing. Understanding how arrays are stored in memory is crucial for grasping their efficiency. The memory address of each element in an array is calculated based on the base address, the element size, and the index. For a one-dimensional array, the address of an element is calculated as address equals base plus I multiplied by w, where I is the index and w is the size of each element. For a two-dimensional array, the formula extends to address equals base plus I times n plus j times w, where I and j are the row and column indices, and n is the number of columns. Arrays support a variety of operations, each with its own time and space complexity. Traversal involves accessing each element of the array, typically to perform operations like printing or modifying elements. Insertion adds a new element at a specific position, whether at the beginning, end, or any index within the array. Deletion removes an element from a specific position, often requiring the shifting of other elements to fill the gap. Search is about finding the position of an element either by its index or value. Finally, update involves modifying the value of an element at a given index. Let's explore the different operations you can perform on one-dimensional array, including adding, removing, and modifying elements. The traverse function is responsible for accessing each element in the array one by one, starting from the first element to the last. This function ensures that every element is processed exactly once, which is crucial when you need to perform operations like printing, modifying, or applying a function to every element in the array. It's a foundational operation in array manipulation, allowing you to interact with each element in a systematic way. The search by value function is designed to find the position of a specific value within the array. It sequentially scans each element of the array and compares it with the desired value. If the value is found, the function returns the index of the element. If not, it returns -1 to indicate that the value does not exist in the array. This function is useful when you need to locate elements within an array without knowing their exact positions in advance. The search by index function retrieves the element located at a specific index within the array. Before accessing the element, it validates the index to ensure it is within the bounds of the array. If the index is valid, it returns the corresponding element. If not, it raises an error. This function is essential for direct access to elements in situations where you know the index but not the value. The update function changes the existing value of an element at a specified index to a new value. Before updating, it checks whether the provided index is within the valid range of the array. If the index is valid, it assigns the new value to the element at that index, effectively modifying the array in place. This operation is useful for altering specific elements within the array while preserving the overall structure. The insert at beginning function adds a new element to the start of the array. It does this by shifting all existing elements one position to the right to make space for the new element at the beginning. The new element is then placed in the first position of the original array. This operation can be costly in terms of time complexity because every element needs to be moved to a new position. The insert at end function appends a new element to the end of the array. Since this operation only involves placing the new element in the next available position, it is typically the most efficient insertion method. No shifting of other elements is necessary, making it a quick and straightforward operation. The insert at index function inserts an element at a specified position within the array. It works by shifting all elements from the specified index onwards one position to the right, creating space for the new element. The new element is then placed at the desired index. This operation affects all elements after the insertion point, making it more time-consuming for large arrays. The delete from beginning function removes the first element from the array by shifting all subsequent elements one position to the left. This effectively reduces the size of the array by 1 and repositions all elements. While the operation is simple, it can be costly in terms of time complexity, especially for large arrays, because every element needs to be moved. The delete from end function removes the last element from the array by simply reducing the length of the array by 1. Since no other elements need to be moved, this operation is very efficient. It is commonly used in stack operations where the last element is the most recent addition. The delete from index function removes an element at a specified index by shifting all elements after that index one position to the left. This eliminates the targeted element and fills the gap left by its removal. Like insertion at a specific index, this operation requires repositioning elements and can be time-consuming for large arrays. Here's a quick look at the time and space complexity of array operations. Traversal takes order of n time since each element is accessed, with order of 1 space as no extra memory is used. Search by value also requires order of n time and order of 1 space. Search by index is efficient, needing only order of 1 time and space. Insertion and deletion can vary, ranging from order of 1 to order of n time, depending on whether the operation is at the beginning, middle, or end, but always with order of 1 space. Thanks for watching. We've covered the basics of one-dimensional arrays today. In our next video, we'll be discussing two-dimensional arrays. Stay tuned.